This is the first video in AP Calculus on separation of variables, which is also part of section 6.1 where we were looking at differential equations and slope fields previously. Today we're going to look at solving differential equations using a process known as separation of variables. But before we get to that, excuse me, I want to go back to a problem that we actually did last semester. We're given a function or an equation like x squared plus y squared equals 25, and if we're asked to find the derivative of that, hopefully you remember this process. This is known as implicit differentiation, when we have to take derivatives of more than one variable in the equation. So the derivative of x squared is 2x, and then the derivative of y squared would be 2y, but remember we convert that to a derivative in terms of x by writing dy dx next to it. And then the derivative of 25 is 0. So at that point, the differentiation is done, but you're not done with the problem until you've solved for dy dx. So we would subtract the 2x to the other side, and we would get 2y dy dx equals negative 2x. And then we would divide by the 2y, and you get dy dx equals negative 2x over 2y, or dy dx equals negative x over y. Now, that should not be anything new. So what if I then posed the question to you of what is the solution to this differential equation? So, well, you know, if you have the derivative negative x over y, then it would have come from an equation like x squared plus y squared equals 25, because that derivative came out to be negative x over y. And in fact, we've previously discussed that anything that's an equation of a circle centered at the origin, which is x squared plus y squared, equal to any constant, like 25, your derivative is going to be negative x over y. So I know that my answer to this equation is already x squared plus y squared equals some constant. But let's look at how we could get there. Well, I would, with any differential equation that's just like a derivative, I would need to integrate in order to find the equation that it came from. But when I'm integrating, all of my integrals so far have ended with dx or something like that, and they've been an integral in terms of x. Not all integrals have to be in terms of x, though. I have both x variables and y variables that need to be integrated here, but I can't integrate them inside the same integral. So what I have to do is I have to have on one side of the equal sign one kind of variable and another side of the equal sign the other kind of variable. So that process is known as separation of variables, where we put all of one variable on one side of the equal sign and all of one on the other. With this particular equation, the other important thing is that you cannot integrate when your dx or dy or d whatever is in the denominator of your expression. So that dx, for example, is an issue right now because it's in the denominator. Well, I could multiply it to the other side, and I would have dy equals negative x over y dx. That pretty much is showing me that my y variables need to be on the left so that that dy doesn't get messed with, and my x variables need to be on the right because now dx is in the right kind of placement that I need it to be in order to integrate. So the only thing that needs to move at this point is that y. And since it's in the denominator, to move it to the other side, I would just multiply it to the other side. I have now separated my variables. All the y's are on one side, all the x's are on the other. So I'm now ready to integrate. So you think through these, just reverse power rule or any other rules that apply to whatever the expression is. So that y is a y to the first. So it would go back to being y to the second. And to figure out the coefficient, remember we do old coefficient divided by new exponent, so it would be 1/2 y squared. And then on the right-hand side, we have negative x, which is actually going to integrate the exact same way, except it'll be negative. So we have negative 1/2 x squared. And this is an indefinite integral, so it does need a plus c on it. You could put one on both sides if you want to, but you really only need one constant in the whole equation. So we tend to put it over with the x variables. I have now integrated. That is a solution to this differential equation. But that's not what I was expecting it was going to be. I thought it was going to be x squared plus y squared equals a constant. So even though this answer is kind of correct, let's think about how we could make it look like x squared plus y squared equals a constant. Well, I could move the negative 1/2 x squared to the left, and it would become positive because I would add it over here. So now I've at least got the constant by itself, but I have these 1/2 that I kind of need to get rid of. Well, if I multiply the entire equation by 2, that gives me x squared plus y squared equals, technically this is 2 times a constant, but 2 times a constant is still just a constant. So now that looks like how we expected it to look, even though that 1/2 y squared equals negative 1/2 x squared plus c would have been okay the way it was written. So like I said, that's a process known as separation of variables. So we're just going to look at some more examples here. So I've got dy dx equals x squared plus x squared y all over 3. So I immediately see that the dx needs to come to the right, which means the y part is going to need to move to the left. However, right now the y is inside this whole fraction and is being multiplied by an x squared. So I can't really move it as long as it's part of all that other stuff. I do happen to notice that I could write it, if I factor out an x squared, this is 1 plus y, like that. Then in terms of separating it, the 1 plus y, since it's being multiplied by the x squared and then divided by 3, I can move the 1 plus y to the left by dividing it. So if I divide it, I get dy over 1 plus y equals, and then the dx I can move to the right by multiplying it. And I pulled the 1/3, or the 3 that was in the denominator, out in front to be a 1/3 because I think that'll make my integration process easier if I don't necessarily think of that as a fraction with x squared in it. Now that I have everything separated, I'm ready to integrate. So on the left-hand side, the 1 over 1 plus y, that is going to be a natural log integral. If you want to, here, I'll write it over here, you can make u be 1 plus y, which means that du, the derivative of that, would be 1 dy. So your integral would be du over u, which is ln of u. So the u is technically absolute value of 1 plus y. Okay, and then on the right hand side, x squared would integrate back to x cubed, and if I do old coefficient divided by new exponent, that's 1/3 divided by 3, which is 1/9, and then plus c. Now here's where we get into a matter of how to write our answers. Most of the time in an FRQ problem, they're not going to be as vague as just to say solve the following differential equation. They will usually say solve the differential equation for y equals f of x. When they write it like that, they want your answer to be in y equals form. So let's talk about how I would solve this to get it into y equals form. So I see my y there, I need to get it by itself. The first thing that I would move away from it would be the ln. I would move the ln by inserting an e to both sides of my equation. That would make the left-hand side just 1 plus y, and you can actually make the absolute value disappear at that point. The right-hand side is e to the 1/9 x cubed plus c. Now notice, that plus c is part of the exponent. It's not out there by itself anymore. So that presents a little conversation that we need to have about properties of exponents. So let me get another color and come over here. E to the 1/9 x cubed plus c. If you remember the concept of adding exponents together, exponents would be added like that if they had originally been two separate bases that were the same, so they were both e's, that were being multiplied together. So we can think of that as then e to the 1/9 x cubed times e to the c. Well, why do we want to do that? Well, e is just a number, and so if you raise it to a c, a constant, a number raised to a constant is still just a number. So we can actually think of that as e to the 1/9 x cubed times a constant. Now sometimes they'll change the variable there just so that you can see that it's different from the plus c that we had. So we can think of that as k e to the 1/9 x cubed. So going back to my equation here, I have 1 plus y equals k e to the 1/9 x cubed. And at this point, all I need to do to get the y by itself is to subtract the 1 to the other side. So I have k e to the 1/9 x cubed minus 1. Notice the minus 1 is not in the exponent like the 1/9 x cubed is. So now, what if we took our solution from that last problem and we then wanted to find the particular solution that satisfies the condition y of 3 equals 5? Well, we had from the last problem the equation y equals k e to the 1/9 x cubed minus 1. So when they give us that initial condition of y of 3 is equal to 5, that means that y is going to be 5 when x is 3. So we're going to use that to solve for our constant k there. So 3 cubed is 27. 27 times 1/9 is going to be 3. So this is e cubed minus 1. So now we're solving for k. So add 1 to the other side. And then divide by e cubed. So k would actually be 6 over e cubed, which makes your equation y equals 6 over e cubed times e to the 1/9 x cubed minus 1, which is technically correct. If this was an FRQ question, you could stop there. If it was multiple choice, they would actually combine those e's together. So if you think about it, that e to the 1/9 x cubed could go in the numerator of our fraction. And when you have two like bases, like those e's there that are being divided, remember we can subtract their exponents. So this is 6e to the 1/9 x cubed minus 3, all minus 1 like that. So that would be your final answer. Now, I want you to pause the video at this point and see if you can manage to solve example 5 on your own. Okay, so I started by separating my variables, but kind of in the rainbow print there, when you have dy over cosecant of y, 1 over cosecant is the same as sine. So I just rewrote that as sine of y dy, and then e to the x dx, which made your integral way easier if you saw that. So then I integrated both sides, got the negative cosine y equals e to the x plus c. Then in blue there, I used the fact that it has to pass through the origin, which is 0, 0, to solve for my value of c. That gave me negative cosine y equals e to the x minus 2. And then from there, I just solved to get y by itself. And this is hopefully what you got for your final answer. So now let's look at this one here. It's a particle motion problem, but again, it's just separation of variables if necessary. So we're given the acceleration function of 3t. They want us to find the function describing the particle's position if it travels at a rate of 2 feet per second when t equals 0 and is 3 feet to the right of the origin when t equals 1. So again, I want you to try pausing the video and seeing if you can work your way all the way to the position function. Alright, so I started with the acceleration function of 3t, rewrote that as a differential equation of dv dt equals 3t, separated my variables, integrated that to get v equals 3/2 t squared plus c. Then I used the information underlined in green at the top of a velocity of 2 feet per second when time is 0 to solve for that c value, which is 2. That takes me to the top of the right column. So I have my velocity function, which I then rewrote as a differential equation in terms of x for my position function, separated my variables, integrated, used the information underlined in red at the top, solved for that c, and it gave me my final position function here. And that wraps up separation of variables.